Tonight, we're going to explore the single furthest point in the future that physics currently allows us to meaningfully describe. A question that sounds, at first, like pure science fiction, but turns out to rest on some of the most rigorously tested laws in all of physics. Not where humanity could survive for another 1,000 years, not another million. We're going to ask something far stranger and far more patient than that. If some distant descendant of our species, or something that grew out of our species, wanted to survive for as long as the laws of physics could possibly allow, trillions of years, and then trillions of trillions beyond that, into a future so remote it can only be described using something called cosmological decades, where would it have to go? And what, exactly, would it have to become just to get there? Most people, asked where humanity might find its final refuge, imagine something warm. A sun-drenched world. A star's gentle, habitable zone. Tonight, we're going to walk that intuition all the way to its breaking point and beyond it. For most of human history, and honestly, for most of scientific history too, survival meant something simple. A planet with water, an atmosphere you could breathe, a sun overhead reliably rising each morning. It's a completely reasonable definition. It's also, according to the physics of the deep future, a definition with an expiration date far, far sooner than most people realize. Then physicists and cosmologists began mapping out, decade by cosmological decade, exactly what happens to matter, energy, and the possibility of complex structure across timescales that make the age of the universe itself look like a single afternoon. The first surprise is how soon Earth's own comfortable habitability actually ends. Not in the 5 billion years most people have heard quoted, but dramatically, shockingly sooner. The second is that the stars popular science has quietly assumed would serve as humanity's next home, burning patiently for trillions of years, turn out to be some of the most violent, hostile environments in the entire cosmos. And the third, the part this whole documentary is really about, is that the very last possible refuge for any form of organized existence isn't a planet, or a star, or even a galaxy. It's something far stranger, far colder, and far more patient than anything currently orbiting anywhere in our night sky. Here's something worth knowing before we go any further tonight. Every stage of this journey rests on real, published physics. Some of it as thoroughly tested as anything in science, some of it, especially toward the very end, resting on careful, honest extrapolation from what we currently know. I'll be clear, throughout, about which is which, because I think that honesty is part of what makes a story this vast actually worth trusting. By the end of tonight, you're going to understand exactly how physicists have mapped the outer boundary of survival itself, and exactly what it would take, in principle, for something descended from us to still be quietly, patiently existing, unfathomably far into the future, long after every star you have ever seen has gone dark. Let yourself settle in. Nothing about tonight's story requires anything of you except to listen. We have a very long journey ahead. Appropriately, perhaps, the longest one this channel has ever attempted. Here is where tonight's journey will take us. We'll begin by redefining what survival even means, once biology itself stops being a reliable long-term strategy. And we'll meet the strange, patient logic of post-biological existence. We'll confront Earth's actual expiration date and discover that the comforting 5 billion year timeline most of us grew up with is, quite simply, wrong. We'll follow the desperate logic of fleeing our dying solar system and sit honestly with just how far current and near-future propulsion technology falls short of what deep future survival will eventually demand. We'll meet the stars popular imagination has quietly assumed will serve as humanity's next refuge. Small, dim, and almost unimaginably long-lived. And then watch that hope shatter against the reality of what these stars actually do to the planets orbiting them. We'll search for refuge in stranger places still, planets with no star at all, drifting alone through the interstellar dark, and moons whose oceans stay liquid not from sunlight, but from the patient, grinding friction of gravity itself. We'll follow the universe itself into its own long decline, through the slow shutdown of star formation, into an age of cold, dead stellar embers, and finally into an age where black holes are the only structures left standing, and we'll arrive together at the single most defensible answer physics currently offers to tonight's title question: a place and a way of existing, stranger than almost anything human imagination has ever seriously proposed. Before we dive in, if the deep, patient timescales of the cosmos are the kind of thing that helps quiet your mind at the end of a long day, consider liking this video or subscribing to the channel. It's a small thing. It costs you nothing. But it helps this kind of slow, patient science storytelling reach the people who need exactly this tonight. Now, let's begin. Before we can go looking for the last place anything could ever survive, we need to slow down and ask what survival would even mean. Once we've traveled far enough into the future that biology itself stops being a workable strategy at all, ordinary biological survival, the kind every living thing on Earth currently depends on, requires a genuinely narrow set of conditions: liquid water, an atmosphere rich in the right mix of gases, and a steady, reliable influx of stellar energy to power it all. It's a wonderfully effective arrangement, here, now, on this planet. But it's also, in the very long run, a temporary one tied entirely to conditions that will not last forever, anywhere. Physicists and philosophers thinking seriously about the deep future have found it useful to describe survival across two separate axes, rather than one single yes or no question. The first axis is the mode of existence, natural versus artificial. Natural survival means a species, or its biological descendants, continuing to live on a planet that passively provides everything needed to sustain them, through ordinary geological and atmospheric processes, the way Earth does for us right now. Artificial survival means something considerably stranger. Consciousness transferred into synthetic substrates, minds running as pure computation rather than biological chemistry, or civilizations built around megastructures engineered specifically to capture and redirect energy in environments no biological body could ever tolerate. The second axis is duration, temporary versus indefinite. And here, physics offers an answer that is, frankly, unforgiving. Because entropy, the measure of disorder in any closed system, only ever increases. True eternal survival turns out to be a flat physical impossibility, no matter how advanced a civilization becomes, no matter what form it eventually takes. The universe is moving, slowly, relentlessly, toward a state physicists call heat death, a condition of total thermodynamic equilibrium where no usable energy remains anywhere for anything to do any work at all. Every form of survival physics can meaningfully describe is, in this sense, ultimately temporary. The only real question is how long it can be stretched, and how cleverly. This is where the theoretical physicist Freeman Dyson offered one of the more genuinely elegant ideas in this entire field. Dyson proposed that in a universe that keeps expanding and cooling, a sufficiently advanced civilization could maximize its own subjective experience of time by deliberately slowing down. Entering long periods of dormancy, waking only briefly to think, to compute, to process a single thought, before returning to hibernation to conserve an ever-shrinking supply of usable energy. As the universe grows colder and colder, such a civilization could, in principle, run its own mental processes on increasingly slower, increasingly cold physical substrates, stretching a fixed, finite reservoir of energy across an almost unbounded span of subjective time. From the outside, such a being might appear to do almost nothing for millions or billions of years at a stretch. From the inside, it might experience that entire stretch as a single, unbroken, perfectly ordinary moment of thought. There's a related idea worth introducing here too, because we'll need it later tonight. The Kardashev scale, originally proposed in 1964 to rank civilizations by how much energy they could harness. a Type I civilization controlling the energy of an entire planet, Type II, an entire star, Type III, an entire galaxy, has since been extended by later theorists to describe hypothetical civilizations far beyond even that scale. These extended categories, sometimes labeled Type IV through Type VI, are defined not simply by how much energy a civilization consumes, but by how far it has spread itself out, physically, across space. A deliberate strategy, these theorists argue, for surviving the kind of catastrophic, localized disasters that could otherwise end an entire civilization in a single, unlucky moment. Keep both of these ideas close as we move forward tonight. The deliberate slowing of subjective time, and the deliberate spreading of a civilization across space. Both will turn out to be essential, not just useful, by the time we reach the true final chapters of this story. There's one more distinction worth drawing clearly before we move forward, because it will quietly shape every single refuge we examine tonight. The word humanity itself starts to feel strained fairly early in a story like this one. Biological bodies, built from ordinary carbon chemistry, are simply not well suited to timescales measured in trillions, let alone the almost incomprehensible cosmological decades we'll eventually reach tonight. So when tonight's story speaks of humanity, surviving into the deep future, it's worth holding that word loosely. Not necessarily flesh and blood descendants in any form we'd recognize today, but something carrying forward whatever we consider essential about ourselves. Our curiosity, perhaps. Our capacity to ask exactly this kind of question and refuse to look away from the answer. Whether that continuity counts as us surviving or something else entirely taking our place is a genuinely open question tonight's story won't try to resolve, only to keep gently in view as the definition of survival itself keeps stretching further from anything biology alone could ever sustain. There's a comforting myth many of us grew up with, repeated so often it feels almost like settled fact. Earth remains habitable until the sun swells into a red giant, roughly 5 billion years from now. It's a genuinely appealing number. Distant enough to feel essentially infinite, close enough to sound scientifically respectable. It is, according to the actual physics of stellar evolution and atmospheric science, simply wrong. Not wrong by a small margin. Wrong by a difference of billions of years, and wrong about which process actually ends Earth's habitability first. Here's what's actually happening, slowly, right now, inside our own sun. As it fuses hydrogen into helium, its core gradually contracts, and its overall energy output climbs steadily by roughly 10% every billion years. That number sounds modest. It is not. A 10% increase in solar luminosity is more than enough to trigger a cascading, irreversible collapse of Earth's climate system. Long, long before the sun ever physically expands into a red giant at all. The first critical threshold, arriving in as little as 1 to 1.1 billion years from now, is something climatologists call the moist greenhouse effect. As the sun's output climbs, Earth's lower atmosphere expands, pushing water vapor higher than it currently reaches, past a natural barrier scientists call the cold trap, and up into the stratosphere. Once water vapor reaches that altitude, high-energy ultraviolet radiation from the sun begins tearing those water molecules apart, splitting them into hydrogen and oxygen. The hydrogen, being so light, simply escapes Earth's gravity entirely, bleeding permanently out into space. Slowly, irreversibly, molecule by molecule, Earth's oceans begin to disappear, not boiled away in a single dramatic event, but quietly, patiently vented into the vacuum of space, never to return. Alongside this slow desiccation, a second, equally devastating process unfolds. Earth's climate has always relied on something called the carbonate-silicate cycle, a natural, geological thermostat where rock weathering draws carbon dioxide out of the atmosphere, while volcanic activity slowly replaces it, keeping the whole system in rough, long-term balance. As temperatures climb, weathering accelerates dramatically, pulling carbon dioxide out of the atmosphere far faster than volcanoes can ever hope to replenish it. Within roughly 1 billion years, atmospheric carbon dioxide will fall below the minimum threshold most plant life actually needs to photosynthesize at all, triggering a mass extinction of nearly every plant on Earth, and, in short order, the collapse of the entire food web those plants have always supported. By roughly the 2 billion year mark, Earth crosses into what scientists call a full runaway greenhouse state. With its oceans gone, and its natural carbon thermostat broken beyond repair, greenhouse gases simply accumulate, unchecked, with nothing left to regulate them. Earth's surface conditions begin to mirror the current hostile reality of Venus. Its remaining moisture boiling away entirely, surface temperatures soaring past 400 degrees Celsius. It's worth remembering, from this same family of documentaries, exactly how hostile that specific environment already is. The most robust landers humanity has ever built, dropped onto the actual surface of Venus, have survived barely more than an hour under conditions like these, before succumbing entirely to the heat and crushing pressure. Only much later, somewhere between 5.5 and 7.5 billion years from now, does the Sun finally exhaust the hydrogen fuel in its core and begin its physical expansion into a genuine red giant, growing large enough to engulf Mercury, Venus, and very likely the scorched, lifeless remnant of Earth itself. A short pause here, if you'd like one. This is a genuinely heavy piece of news to sit with, even at this comfortable geological distance. Take a slow breath. Nothing about tonight's timeline requires anything of you right now, tonight, in this exact moment. We'll continue when you're ready. Here is the honest, corrected timeline, stated plainly. Earth's habitability doesn't end in 5 billion years. It ends in roughly 1 billion years, when the oceans begin their irreversible escape into space, a full 4 billion years earlier than the comforting popular myth suggests. Whatever conversation, humanity, or whatever descends from humanity has about leaving this planet permanently needs to happen on a timeline dramatically shorter than most of us have ever been taught to imagine. It's worth sitting, briefly, with just how much runway that still actually leaves us, even with the corrected number. 1 billion years is, by any ordinary human measure, an almost incomprehensible span of time. Roughly 200 times longer than complex, multicellular animal life has existed on Earth at all. Every human civilization that has ever risen and fallen, every war, every empire, every technological revolution from the first stone tool to whatever device you're listening to this on right now, fits inside a sliver of time thousands of times smaller than the runway we've just described. The correction from 5 billion to 1 billion years is genuinely significant, scientifically. It is not, in any practical sense, a cause for tonight's kind of urgency. If Earth's habitability genuinely ends within roughly 1 billion years, the obvious next question is simple. Could we just leave? Pack up and go somewhere else, the way humanity has always eventually done when one place stopped working? The honest answer, examined closely, is considerably more complicated than science fiction tends to suggest. Every spacecraft departing Earth inherits the planet's own orbital velocity around the Sun, roughly 30 kilometers per second. To escape the solar system entirely, a spacecraft needs to add only about 12 more kilometers per second to that inherited speed, reaching a solar escape velocity of around 42 kilometers per second. That part, at least, is within reach of technology either already flying or plausibly just a few decades away. The real barrier is the same unforgiving piece of mathematics we've encountered before in this kind of story. The Tsiolkovsky rocket equation, which relates how much a spacecraft's velocity can change to the efficiency of its engines and the ratio between its fueled and unfueled mass. Traditional chemical propulsion remains severely limited by this equation. The Saturn V rocket, for historical comparison, required a propellant mass fraction of roughly 90%, leaving a final payload fraction of less than 2% for the actual cargo it delivered toward deep space. Even the most advanced modern reusable systems, aiming for payload capacities of 100 to 200 tons, remain fundamentally bound by the same chemical limits. The raw energy density of burning liquid oxygen and methane, a ceiling no amount of clever engineering can push past. Beyond raw propulsion, interplanetary and interstellar navigation demands a level of precision that borders on the unbelievable. A velocity error of just 1 meter per second at the moment of departure from Earth, again, roughly an ordinary human walking pace, can compound over a long enough journey into a trajectory miss of over 2,800 miles at the intended destination, requiring costly, fuel-hungry mid-course corrections just to stay on target. It's worth pausing on what this precision requirement actually means for a journey measured not in months, like a trip to Mars, but in centuries or millennia, the kind any genuine interstellar migration would require. Every source of error compounds not just once, but continuously across the entire duration of the flight. Tiny gravitational perturbations from passing stars, minuscule imperfections in a propulsion system's thrust, even the slow, cumulative effect of interstellar dust striking a spacecraft's hull over thousands of years. A margin of error that seems entirely acceptable over a 9-month transit to Mars could, stretched across a multi-century journey to another star system, compound into a missed distance measured not in miles, but in entire star systems. A spacecraft arriving, after centuries of travel, at empty space, having missed its target by a margin larger than the very system it was aiming for. To genuinely reach interstellar velocities, fast enough to matter across the kind of timescales tonight's story is really about, humanity would need propulsion technology considerably beyond anything currently operational. Chemical rockets, like the ones currently flying, offer high thrust but a comparatively feeble efficiency, and remain limited essentially to travel within our own solar system. Nuclear thermal propulsion, where a fission reactor superheats liquid hydrogen for improved efficiency, remains in development, and in one high-profile case. A joint program called Draco, aiming to test a working reactor in orbit, faced indefinite delays and effective cancellation in 2025, undone by a mixture of regulatory hurdles, the genuine complexity of testing a nuclear reactor in space, and the sheer, unglamorous cost efficiency of newer, reusable chemical rockets, making the whole program harder to justify. Nuclear electric propulsion, where a reactor instead generates electricity to power efficient plasma thrusters, continues to see genuine laboratory progress. Engineers have recently tested a prototype thruster generating 120 kilowatts of power using lithium metal vapor, a promising, if still early, step forward. But to actually cross interstellar distances, within any time frame a civilization could meaningfully plan around, humanity will eventually need something considerably more exotic still. Fusion drives, or matter-antimatter annihilation propulsion, technologies that remain, for now, almost entirely theoretical, alongside heavily shielded, fully self-sustaining life support systems capable of operating entirely autonomously for millennia at a stretch. This is the sobering truth sitting underneath tonight's opening act. Even in the comparatively near term, a single billion years, a mere eye blink by the standards of the rest of tonight's story. Humanity does not currently possess the technology needed to simply relocate somewhere else, at any meaningful scale, should Earth's own habitability genuinely begin collapsing on schedule. And this is only the very first hurdle in a journey that, as we're about to discover, gets dramatically stranger and dramatically more demanding from here. Let's suppose, for the sake of tonight's story, that humanity, or something descended from humanity, eventually solves the propulsion problem from the last chapter and successfully reaches another star system. Which star should it actually choose? Sun-like stars, the comfortable, familiar kind currently warming Earth, are, cosmically speaking, disappointing long-term investments. A star like our own Sun has a total main sequence lifespan of roughly 10 billion years before it exhausts its core hydrogen and begins the same red giant expansion discussed a few chapters ago. For a civilization thinking not in centuries, but in cosmological decades, 10 billion years is barely a down payment. There is, however, a category of star that dramatically outlasts every Sun-like star in the galaxy by a truly staggering margin. Red dwarfs, small, dim, low-mass stars, make up somewhere between 70 and 75% of the Milky Way's entire stellar population, by far the most common type of star in existence. Their defining trait is their small mass, typically somewhere between 8 and 45% of our own Sun's mass, which corresponds to a much lower core temperature and a dramatically, almost unbelievably slower rate of nuclear fusion. Here's the detail that made red dwarfs, for a long time, seem like the obvious long-term answer to tonight's entire question. Because they are fully convective throughout their interior, meaning their material continuously churns and mixes rather than settling into separate, static layers. Red dwarfs burn through their available hydrogen fuel with remarkable efficiency, drawing fresh fuel down into the core as fast as it's consumed. This efficient fuel use, combined with their inherently slow rate of fusion, grants them a lifespan measured not in billions of years, but in trillions. While our own Sun will burn for roughly 10 billion years total, a small red dwarf can continue fusing hydrogen for several trillion years, hundreds of times longer than the entire current age of the universe itself. As every other kind of star gradually exhausts itself and goes dark, red dwarfs will be the very last active, naturally shining stars left anywhere in the cosmos, making them, on paper, the obvious final refuge for any civilization still relying on ordinary starlight. It's a beautiful piece of astrophysics. It is also, once you look closer at what actually happens on a planet orbiting one of these stars, a genuinely cruel piece of false hope. Because red dwarfs are so dim, any planet hoping to sit in their habitable zone, the narrow band of distance where temperatures allow liquid water, has to orbit dramatically closer than Earth sits to our own Sun, somewhere between 10 and 20 times closer, depending on the specific star. And that extreme proximity creates an almost unavoidable consequence: tidal locking. Just as our own moon always shows Earth the same face, a planet orbiting this close to its star becomes gravitationally locked into always showing that star the exact same hemisphere. One side permanently, eternally baked under constant daylight, the other side locked in permanent, freezing darkness forever. Advanced climate modelling suggests a sufficiently thick, dynamic atmosphere could, in principle, redistribute enough heat to prevent the night side from simply freezing solid. But maintaining an atmosphere thick and stable enough to manage that redistribution, this close to an active star, turns out to be exceptionally difficult. And difficult turns out to be an understatement once you account for exactly how red dwarfs actually behave. Young red dwarfs, still settling into their long, stable lifespan, are extraordinarily magnetically active, regularly unleashing massive stellar flares and enormous eruptions of high-energy X-ray and ultraviolet radiation far more violently and far more frequently than a calmer, sun-like star ever would. This radiation doesn't simply warm a planet's surface. It physically tears apart atmospheric molecules, driving an aggressive, ongoing process of atmospheric escape that can strip away a planet's oxygen, nitrogen, and hydrogen systematically over the course of just a few million years. And here's the detail that closes this chapter's door most firmly of all. Even ancient, long-settled red dwarfs are not the calm, gentle refuges popular imagination assumes them to be. Recent observations of Barnard's star, a red dwarf roughly 10 billion years old, among the oldest, most settled stars anywhere near us, found that despite its extreme age, it continues to emit scorching, high-energy flares roughly a quarter of the time. 10 billion years of supposed stability, and the star is still capable of stripping away a freshly regenerated atmosphere before it ever has the chance to properly form. A short pause here, if you'd like one. It's a genuinely disappointing turn after building red dwarfs up as the great hope of the deep future. Let that disappointment settle, gently, and we'll continue. The assumption that red dwarfs offer a safe, calm harbour for the deep future turns out to be, on close inspection, almost entirely backward. They are not humanity's gentle, patient saviours. They are some of the most persistently violent engines in the entire galaxy, wrapped in a deceptively long, deceptively patient lifespan. It's a genuinely humbling lesson in how misleading a single number, trillions of years of lifespan, can be when it's allowed to stand in for an entire environment's actual habitability, without anyone examining what that lifespan actually costs the planets caught orbiting nearby. If the stars themselves turn out to be this hostile, even the patient, long-lived ones, perhaps the answer isn't to seek out starlight at all. Perhaps, counterintuitively, the safest place in the universe is somewhere with no star and no light whatsoever. Scattered throughout our galaxy, and very likely throughout every other galaxy, are planets called rogue planets. Worlds that were once gravitationally bound to a star, before violent gravitational interactions with other planets, or passing stars flung them permanently out of their original system, sending them drifting, alone, through the vast, empty spaces between stars with no host star to call their own ever again. On the surface, a rogue planet sounds like the worst possible refuge imaginable. Without a star to warm it, surface temperatures would plunge to somewhere near absolute zero. A frozen, lightless, apparently lifeless wasteland, drifting endlessly through the interstellar dark. But the surface, it turns out, may not be where the story actually happens. If a rogue planet possesses a sufficiently dense, radioactive core, the same kind of natural radioactive decay that keeps Earth's own interior molten today, the continuous heat generated by that decay, combined with leftover heat from the planet's original formation billions of years earlier, can sustain a genuine, liquid water ocean trapped safely beneath a thick, insulating shell of surface ice. The ice itself becomes the protection, rather than the obstacle. A barrier several kilometers thick, sealing a warm, stable ocean away from the lethal cold and radiation of open space, indefinitely. There's an even stranger possibility some theoretical models point toward. A sufficiently massive rogue planet, one that managed to hold onto a thick, primordial hydrogen atmosphere from its original formation, could generate enough atmospheric pressure and greenhouse effect entirely on its own, with no star involved at all, to keep its actual surface warm enough for liquid water to exist directly, without needing any ice shell for insulation whatsoever. A planet, in other words, that manufactures its own climate entirely internally, floating in the permanent dark, needing nothing at all from the outside universe to remain habitable. For a civilization capable of drilling through an ice shell, or adapting to an existence built around chemistry rather than sunlight, the same basic strategy already used by certain ecosystems clustered around hydrothermal vents, deep in Earth's own oceans, entirely independent of sunlight even today. A rogue planet offers something genuinely remarkable: complete, total insulation from stellar flares, from the eventual death of any host star, and from the wider radiation environment of the galaxy as a whole. No star to eventually swell into a red giant. No flares to strip away a hard-won atmosphere. No tidal locking, because there's no star to be locked toward in the first place. Just a quiet, dark, stable world drifting patiently through the void entirely on its own terms. It's worth sitting with how deeply this subverts one of the most basic instincts built into us by billions of years of evolution. The instinct to seek out sunlight, to associate warmth and light with safety and cold darkness with danger. Tonight's story suggests that instinct, so reliable here on Earth, may be exactly backward, once you're planning not for a human lifetime, but for the deep cosmological future. The star that seems to promise safety may be the very thing that eventually destroys you. The lightless void that seems to promise nothing at all may, quietly, be the safest place in the entire galaxy. There's a particular kind of quiet worth imagining here before we move on. Picture such a planet, drifting alone through the vast spaces between star systems, utterly invisible from any distance, utterly silent, its ice-locked ocean glowing faintly with bioluminescent light generated by whatever ecosystem has taken root around its own hydrothermal vents. An entire, complete biosphere, thriving in total, permanent darkness, with no sun, no sky, no horizon, and no concept of day or night at all. It would be, by any reasonable human standard, one of the strangest possible homes imaginable. It might also, according to everything tonight's story has covered so far, be one of the most durable. There's one more natural refuge worth exploring before we leave planets and moons behind entirely. A mechanism that doesn't rely on a star's light at all, and doesn't rely on a planet's own leftover radioactive heat either, but on something considerably stranger, the patient, grinding friction of gravity itself. In systems built around massive gas giants, think of Jupiter's moon Europa or Saturn's moon Enceladus, both places already suspected of hiding genuine oceans beneath their icy surfaces. A phenomenon called tidal heating provides a remarkably stable, remarkably long-lasting source of internal warmth. As a moon orbits a massive planet along a slightly elliptical, rather than perfectly circular, path, the planet's gravity doesn't pull on it evenly. It flexes and stretches the moon's interior, slightly, with every single orbit, converting a small amount of that gravitational energy directly into heat through simple internal friction. The same basic principle behind repeatedly bending a metal paperclip until it grows warm in your hand. Here's what makes this mechanism genuinely remarkable for tonight's story, more than any other refuge examined so far. It doesn't depend on a star at all, meaning it's completely immune to everything discussed in the last 2 chapters. No risk from stellar flares, no risk from a dying star's eventual expansion, no dependence whatsoever on the star surviving, or even existing in the first place. Even after a host star has fully died, expanded, shed its outer layers, and collapsed down into a cold, compact white dwarf. The orbital relationship between an outer gas giant and its moons can remain largely, structurally undisturbed, continuing to generate tidal friction for an extraordinarily long time afterward, entirely independent of whatever happened to the star at the center of the system. A sufficiently advanced civilization, biological, artificial, or something in between, could migrate directly into one of these deep, tidally heated oceans, protected by kilometers of overlying ice from cosmic radiation, from micrometeorite impacts, from the total vacuum of space itself, while drawing continuous, reliable energy from hydrothermal vents driven entirely by the moon's own internal flexing. Of every natural refuge examined in tonight's story so far, this combination, deep insulation, combined with a genuinely long-lasting internal heat source independent of any star, makes subsurface, tidally heated oceans among the most stable, most enduring natural environments likely to exist well into the later chapters of the universe's own story. There's a particular elegance worth noticing in this specific mechanism, one that sets it apart from every other refuge examined tonight. Red dwarfs offer longevity, but that longevity comes wrapped in violence. Rogue planets offer safety, but that safety is finite, tied to a radioactive clock that eventually runs down. Tidal heating offers something closer to both at once, a genuinely long-lasting energy source, sustained not by anything that can flare or erupt or eventually exhaust itself in the way radioactive decay does, but by the simple, mechanical, endlessly repeating motion of an orbit. As long as the orbital relationship between moon and planet remains stable, the heating continues, patiently, indefinitely, requiring nothing from the outside universe at all except the continued, quiet persistence of gravity itself doing exactly what gravity has always done. Every natural refuge examined so far, red dwarfs, rogue planets, tidally heated moons, eventually runs into its own expiration date. Genuine, indefinite survival, stretched across the truly deep future, will almost certainly require civilizations to stop relying on naturally occurring environments altogether and begin building their own. Vast artificial habitats, sometimes imagined as O'Neill cylinders, rotating structures generating artificial gravity through spin, or Dyson swarms, immense constellations of solar collectors encircling a star to capture nearly all of its energy output. This represents a genuine turning point in tonight's story, worth naming clearly. Everything discussed up to this chapter has been a search for a place, somewhere already existing, somewhere nature happened to provide, that a civilization might simply move into and inhabit. From here forward, the story shifts. Survival stops being a search and becomes a construction project, one that never really finishes, requiring active maintenance, active engineering, and active problem solving indefinitely for as long as anyone remains to do the work. But building something built to last, not for centuries, but for millions or even billions of years, runs headlong into three separate, deeply unforgiving engineering constraints worth walking through slowly, because each one echoes something we've already discussed tonight in an entirely different context. The first is thermal management. In the vacuum of space, heat cannot be carried away through conduction or convection, the way it constantly, invisibly is here on Earth. It can only be radiated away, directly, as electromagnetic energy. And the rate at which any object can radiate heat is governed by a precise physical relationship called the Stefan-Boltzmann law, where radiated power scales with the fourth power of an object's temperature. To keep an artificial habitat at comfortable, biologically livable temperatures, engineers would need genuinely massive radiator arrays, built from advanced materials specifically engineered to shed heat efficiently, simply to prevent the habitat from slowly cooking itself alive, using nothing more than the waste heat generated by its own internal computers and reactors. Interestingly, a post-biological civilization, one no longer tied to comfortable biological temperatures, could actually design significantly smaller, lighter habitats by choosing to operate at higher internal temperatures. Because hotter radiators, following that same Stefan-Boltzmann relationship, can shed a given amount of heat using dramatically less surface area than cooler ones require. The second constraint is computational autonomy. And here, tonight's story circles directly back to something we've discussed in earlier documentaries from this very channel: the vulnerability of ordinary microprocessors to cosmic radiation. High-density modern computer chips, the kind running billions of transistors at multi-gigahertz speeds, are exceptionally vulnerable to single-event upsets. Random bit flips caused by high-energy cosmic ray particles striking a chip's delicate circuitry. Spacecraft hardware instead relies on specially hardened processors, running at dramatically slower speeds but featuring extensive built-in redundancy, specifically engineered to survive exactly this kind of radiation damage over long mission durations. The consequences of getting this wrong have already, tragically, played out in real spaceflight history, twice in remarkably similar ways. In 1999, the Mars polar lander was destroyed when an ordinary mechanical vibration, generated by its own landing legs deploying, sent a stray signal that its onboard computer misread as confirmation of touchdown, prematurely shutting down its descent engines while still 40 meters above the actual surface. In 2016, the European Schiaparelli lander suffered an almost identical fate. A brief, 1-second burst of bad sensor data, caused by ordinary parachute oscillation, convinced its navigation computer it had already descended below ground level, triggering a fatal, premature release of its parachute at far too great a height. Both failures, worth remembering, were survivable in principle, and both happened anyway, because a fully autonomous system, operating with no possibility of human correction, has absolutely no margin for a single bad assumption made at exactly the wrong split-second moment. Here's the sobering question this history raises, and it's genuinely worth sitting with. If humanity, at the very peak of our current engineering capability, still cannot reliably build a landing sensor capable of surviving a single second of unexpected mechanical vibration, how could any civilization possibly build an autonomous system, a generation ship or an artificial habitat, capable of correctly, flawlessly managing its own survival for millions or billions of years without a single catastrophic error, entirely without any possibility of outside human intervention at all? Communication delays across interplanetary distances already range from 3 minutes to Venus, up to 52 minutes to Jupiter, and a full 24 hours to reach a spacecraft as distant as Voyager 1. Delays that already make real-time human correction physically impossible at planetary scales. At interstellar, or eventually intergalactic distances, the concept of checking in on a distant habitat becomes not merely inconvenient, but entirely, permanently meaningless. The third constraint is energy and resource generation. The challenge of actually powering a habitat indefinitely without ever running out of fuel. In the near term, radioisotope generators, like the plutonium-powered units currently keeping Mars rovers alive through the brutal cold of the Martian night, offer a genuine template. Reliable, decades-long power with no moving parts. Longer-term, in-situ resource utilization. Manufacturing air, water, and fuel directly from local raw materials, exactly the way an experiment aboard the Perseverance rover has already successfully demonstrated on Mars, converting the planet's own thin atmosphere into breathable oxygen, becomes an absolute necessity rather than a mere convenience. And eventually, as stars themselves begin to die out across the galaxy, artificial habitats will need to scale these same basic principles up dramatically, relying entirely on internal fusion reactors, fusing progressively heavier elements as lighter, more efficient fuels run out, extracting steadily diminishing energetic returns until, eventually, all available matter has been fused into iron. The single most stable atomic nucleus in existence, and a dead end for any further fusion reaction whatsoever. Let's take a genuinely deep breath here, because tonight's story is about to leave behind anything resembling a human timescale entirely, and step into territory measured not in years, or even billions of years, but in something physicists call cosmological decades. A scale where each step represents a power of 10 years, 10 to the 18th, 10 to the 40th, 10 to the 100th, numbers so large that the difference between a very long time and an almost incomprehensibly longer time stops being something ordinary language can really capture. Let's try, briefly, to actually feel the shape of this scale, rather than just hear the notation. The universe, right now, is roughly 13.8 billion years old, a number we can, with real effort, hold in our minds, because it's only about 10 to the 10th years. The stelliferous era, the age of stars we currently live inside, won't fully end until somewhere around 10 to the 14th years, 100,000 times longer than the universe's current age. The degenerate era we're about to enter stretches on to somewhere around 10 to the 40th years. And the black hole era, where tonight's final answer lives, extends out toward 10 to the 100th years, a number so large that if you tried to write it out in full as an ordinary decimal number, one followed by 100 zeros, it would already dwarf, by many, many times over, the total number of atoms estimated to exist in the entire observable universe today. We are not simply talking about a long time. We are talking about a scale where the tools ordinary human intuition uses to compare durations simply stop functioning at all. Astrophysicists Fred Adams and Gregory Laughlin, in a landmark framework known as the 5 Ages of the Universe, mapped out exactly this kind of timeline, tracing the universe's story from its explosive birth all the way to its final, quiet end. We currently live in what they call the stelliferous era, the age of stars, the only period during the universe's entire existence when stars actively form, shine, and support the kind of complex chemistry that makes biological life possible at all. This era, remarkably, is still just beginning. It won't end until the very last red dwarfs. Those same trillion-year lifespan stars we spent an earlier chapter learning to distrust finally, patiently exhaust their own hydrogen fuel, an event so distant in the future it dwarfs the current age of the universe by a factor of hundreds. Once that happens, the universe enters what Adams and Laughlin call the degenerate era. Star formation, the process that has defined the visible universe since almost its very beginning, simply stops permanently. No new stars will ever ignite again. What remains, scattered throughout every galaxy, are nothing but stellar corpses. Brown dwarfs that never quite achieved fusion in the first place. White dwarfs, the slowly cooling embers of stars like our own sun, neutron stars, and black holes. Look up into the night sky during this era, from anywhere in the universe, and you would see, essentially, nothing at all. A sky gone permanently, entirely black, invisible light, for the first time since the universe's earliest infancy. It isn't quite absolute silence, though. Occasionally, rare collisions between pairs of orbiting brown dwarfs will briefly pool together enough combined mass to spark a short, low-intensity burst of hydrogen fusion. A fleeting, accidental candle, flickering briefly in an otherwise permanently dark universe before fading out again. And white dwarfs, the cooling remnants of stars like our own sun, though no longer actively fusing anything, will continue radiating a faint, residual heat for trillions of years, left over from their earlier, more active lives. There's a genuinely strange detail buried in this era, worth pausing on. Some theoretical models suggest that cold white dwarfs, drifting through their galaxy's own halo, will slowly accrete tiny amounts of dark matter. The mysterious, invisible substance that makes up roughly a quarter of the universe's total mass, detectable only through its gravity. If dark matter particles happen to be their own antiparticles, as some leading theoretical models propose, then the accumulation and eventual annihilation of these particles inside a white dwarf's core could generate a small but genuinely continuous trickle of internal heat, keeping these ancient, cooling stellar embers marginally warmer than the surrounding void, offering, in principle, one final, meager but remarkably long-lasting thermal gradient for any civilization patient enough and advanced enough to still be there to harvest it. Surviving inside the degenerate era, with fusion no longer a viable source of new energy anywhere in the universe, requires an entirely different survival strategy. One that trades chemistry and nuclear fusion for something considerably more brutal and direct, gravity itself. The most promising approach involves accretion disks, swirling clouds of matter, slowly spiraling inward around a compact object like a white dwarf or neutron star. As this material falls deeper into the object's steep gravitational well, internal friction within the disk heats it to temperatures reaching millions of degrees, releasing genuinely enormous amounts of energy in the process. An efficiency considerably higher than even nuclear fusion can achieve, simply by exploiting the raw, brutal power of a deep gravitational field rather than any chemical or nuclear reaction at all. But even this strategy has a genuine, honestly uncertain expiration date, one that hinges on a single unresolved question in fundamental physics, grand unified theories, ambitious frameworks attempting to merge several of the fundamental forces of nature into one single, unified description. Predict that protons, the basic building blocks sitting at the center of every atomic nucleus in existence, are not, in fact, perfectly stable. According to these theories, protons should eventually decay on a timescale so long it makes even the degenerate era's own duration look brief by comparison. If this prediction holds true, every remaining scrap of ordinary matter in the universe, every dead star, every rocky planetary remnant, every physical structure any surviving civilization has ever built, would, eventually, simply dissolve away into a faint mist of positrons, electrons, and photons, with nothing solid left standing anywhere. It's worth being genuinely honest here, because this is one of the more important uncertainties in tonight's entire story. Proton decay has never actually been observed by any experiment, anywhere, despite decades of dedicated searching. Its predicted timescale remains a matter of theoretical extrapolation, not direct measurement. If it turns out protons are, in fact, perfectly stable, an entirely different fate awaits ordinary matter instead. An even stranger process called quantum tunneling, unfolding across timescales longer still, would gradually convert all remaining matter into iron through an almost unimaginably slow, patient process of cold nuclear fusion and fission, eventually locking every remaining scrap of the universe's matter into solid, inert iron stars. In that particular scenario, a sufficiently advanced civilization could, in principle, actively mine these iron stars, using enormous particle accelerators to forcibly manufacture antimatter directly from that iron, enabling matter-antimatter annihilation, the single most efficient form of energy conversion permitted anywhere in known physics, as one final, finite, but genuinely powerful energy source, before the universe's story moves on to its next, even stranger chapter. Eventually, whether through proton decay or the almost equally patient process of quantum tunneling into iron, essentially all of the universe's remaining ordinary matter will have dissolved or transformed away. What's left, according to Adams and Laughlin's timeline, ushers in what they call the black hole era, a period where black holes become, quite literally, the only macroscopic structures remaining anywhere in the entire cosmos. Far from being simple destroyers, black holes turn out to be genuinely remarkable energy reservoirs, and physicists have already worked out, in careful theoretical detail, how a sufficiently advanced civilization could actually harvest that energy. One method, called the Penrose process, exploits a region just outside a rotating black hole's event horizon, called the ergosphere, where space-time itself is dragged along by the black hole's own rotation. By carefully dropping a mass into this region and splitting it in two, one fragment can be sent falling past the event horizon forever, while the other fragment is ejected back outward, carrying away more kinetic energy than the original object possessed, effectively siphoning off a fraction of the black hole's own rotational energy, borrowed rather than destroyed. But even black holes, the most extreme, most gravitationally powerful objects the universe contains, are not permanent. Through an extraordinarily subtle quantum effect occurring right at their event horizon, black holes very slowly emit what's called Hawking radiation, named for physicist Stephen Hawking, who first worked out the theoretical mechanism. Because this radiation is inversely proportional to a black hole's mass, an enormous, supermassive black hole emits only the faintest possible trickle of energy at a temperature only barely above absolute zero. A sufficiently advanced, sufficiently patient civilization could construct a vast, enclosing megastructure around such a black hole, specifically engineered to capture that faint, continuous trickle of Hawking radiation, converting it into whatever meager but genuinely reliable power such a civilization would need to continue existing at all. There's something worth pausing on here in the sheer scale of patience this would require. A supermassive black hole, of the kind found at the center of galaxies like our own, is expected to take somewhere in the neighborhood of 10 to the 100th years to fully evaporate through Hawking radiation alone, a number that dwarfs, by an almost unimaginable margin, every other timescale discussed so far tonight, including the entire multi-trillion-year stelliferous era of actively burning stars. A civilization gathered around such a black hole would not be waiting out a difficult decade, or even a difficult few billion years. It would be settling in for a wait longer than every previous era of the universe's entire history, combined and multiplied many times over. An act of patience that makes even the most extreme forms of human endurance look, by comparison, instantaneous. And here is the strange, almost poetic detail buried inside the physics of the black hole's own evaporation. As it loses mass, ever so slowly, over unimaginable stretches of time, it evaporates progressively faster and progressively hotter, right up until the very final moment of its existence. Meaning any civilization gathered around a dying black hole would eventually experience one final, genuinely brilliant flash of concentrated energy, right at the very end, before the black hole vanishes entirely and the light goes out for good. Once every black hole in the universe has finally, completely evaporated away, the universe enters its fifth and final chapter in the Adams and Laughlin framework, what they call the Dark Era. There is nothing dramatic left to describe here, and that absence of drama is, in its own way, the entire point. No stars, no stellar remnants, no black holes. Only a vast, cold, uniform bath of the lowest energy particles physics allows. Scattered photons, ghostly neutrinos, and fleeting, unstable pairs of positronium, briefly forming and immediately dissolving, with nothing left anywhere capable of sustained, organized structure of any kind. This is heat death, arriving in its final, absolute, unambiguous form. Total thermodynamic equilibrium, precisely the state the second law of thermodynamics has been patiently, relentlessly building toward since the very first fraction of a second after the Big Bang. No usable energy gradients remain anywhere for anything to draw on. No temperature differences exist to power any conceivable engine, biological or artificial. Survival, by any definition physics can meaningfully offer, becomes a flat, unambiguous impossibility for anything, anywhere, ever again. It's worth stating this final boundary plainly, because tonight's entire story has been building toward locating it precisely. There is no candidate refuge beyond this point. Not a stranger form of matter, not a cleverer form of energy harvesting, not a more patient, more slowly thinking civilization. The Dark Era isn't simply difficult to survive in. It is the physical absence of the very thing survival, in any form, has ever required. A usable difference between here and there, between now and later, between hot and cold. Once that difference disappears completely, there is, by definition, nothing left for anything to do at all. Let's gather every candidate refuge tonight's story has examined, and rank them, honestly, from the nearest term option to the absolute outer limit of what physics can currently describe. At the fifth rank sits the subsurface ocean of a gas giant's moon, sustained by tidal heating, insulated by kilometers of ice, genuinely stable through much of the remaining stelliferous era, but ultimately dependent on the long-term orbital stability of its system and the eventual fate of whatever star that system still orbits. At the fourth rank sits the red dwarf habitable zone, offering trillions of years of raw stellar longevity, undermined by violent flares and merciless tidal locking, a refuge that looks perfect on paper and turns out to be one of the more hostile options actually available. At the third rank sits the internal ocean of a rogue planet, insulated entirely from stellar violence by the simple absence of any star at all, ultimately limited only by the slow, patient decay of its own internal radioactive heat source, eventually leading to a total, permanent planetary freeze. At the second rank sits a white dwarf accretion swarm, deep into the degenerate era, harvesting gravitational energy from infalling debris and the faint trickle of dark matter annihilation, requiring massive, continuous active thermal management, and ultimately still vulnerable to the same uncertain question of proton decay that looms over every form of ordinary matter in this scenario. And at the very first rank, the single most defensible answer physics currently offers to tonight's title question, sits a Hawking radiation collector sphere built around a supermassive black hole deep into the black hole era itself, roughly 10 to the 100th power years from now. Here is what that answer would actually mean, in practice, for whatever remains of humanity by that unimaginably distant point. long after the last red dwarf has gone dark, long after every proton making up every planet, star, and biological body has potentially decayed into nothingness, black holes remain the sole reservoirs of usable energy left anywhere in existence. A post-biological, almost certainly non-biological form of intelligence, quite possibly built from forms of matter we don't yet understand, or organized in ways that bear no resemblance to any current human technology, could construct a vast enclosing structure around one of these dying black holes, drawing in its last faint trickle of Hawking radiation as its only remaining source of power. To make that trickle of energy last as long as physically possible, such a civilization would need to obey something called Landauer's principle, a fundamental physical limit on the absolute minimum energy required to process even a single bit of information. Operating at temperatures only barely above the surrounding vacuum itself to maximize thermodynamic efficiency, this civilization's own subjective experience of time would need to slow to an almost unimaginable crawl. For every single second of conscious thought experienced from the inside, millions of years might pass on the outside. An echo, on a truly cosmic scale, of the same hibernation strategy Freeman Dyson proposed all the way back in Chapter 1, stretched now to its absolute physical limit. And then, finally, as the black hole approaches the very last moments of its own evaporation, its Hawking radiation output would begin accelerating dramatically, faster and hotter, right up until the instant it disappears completely. Whatever remains of this final civilization would experience one last, genuinely brilliant surge of usable energy. A final campfire, gathered around the last dying ember the universe has left to offer, before the black hole vanishes entirely and the lights of the universe go out permanently for the very last time. There is no physical or theoretical model, currently known to science, that permits survival in any form beyond that final moment. It's worth sitting, one more time, with exactly how alien this final refuge actually is, compared to everything tonight's story began with. We started this journey looking for a planet, something with water, air, and a sun overhead. The same basic recipe every biological refuge examined tonight has needed, in one form or another. We end it with something that has no planet, no water, no air, and no sun at all. Only a dying gravitational singularity and a civilization patient enough and strange enough to have shed every single one of those original requirements, one chapter at a time, across a timescale so long that the word civilization itself starts to feel almost too small, too human, to properly describe whatever is actually still there, thinking its slow, patient, final thoughts. There's a specific image worth holding on to here, drawn directly from the physics itself. Picture a structure, built from forms of matter we can't currently name, encircling a black hole in absolute silence and absolute cold, its inhabitants. If inhabitants is even the right word anymore, running at a subjective pace so slow that a single thought might stretch across millions of external years. From the outside, such a structure would appear to do nothing at all, forever, an object of total, motionless stillness. From the inside, across that same span, a single idea might be quietly, patiently, being turned over, examined from every angle, in no particular hurry at all, because hurry, by that point, would have become entirely meaningless. The last trace of urgency dissolved along with everything else that once made survival feel urgent in the first place. Before we move into tonight's closing chapters, I want to pause and be honest with you about something, because tonight's story spans a genuinely enormous range of scientific confidence, from rock-solid, thoroughly tested physics to careful, informed, but still genuinely speculative extrapolation. It's worth separating the two clearly, rather than presenting all of it with equal certainty. On solid ground, resting on established, thoroughly verified physics, the timeline for Earth's own demise. The moist and runaway greenhouse transitions we discussed earlier tonight is based on standard, well-tested solar models and established climatological thermodynamics, not speculation. The extraordinary longevity of red dwarf stars, the mechanics of tidal locking, and the punishing constraints of the rocket equation are direct, undeniable consequences of classical mechanics and stellar physics, verified repeatedly through direct observation. The thermal limits governing spacecraft in a vacuum and the genuine vulnerability of microprocessors to cosmic radiation are demonstrated empirically by space agencies on a routine, ongoing basis. And the heat death of the universe itself follows directly, unavoidably, from the second law of thermodynamics. Among the most thoroughly tested, most repeatedly confirmed principles in all of physics. On considerably less certain ground, the specific existence and timing of the black hole era and the dark era that follows it both rely heavily on proton decay actually occurring as predicted. While grand unified theories do predict it, proton decay has never once been directly observed by any experiment, despite decades of dedicated searching, placing only an empirical lower limit on how long, at minimum, a proton's lifespan must be, without confirming whether decay happens at all. If protons genuinely never decay, tonight's proposed degenerate era